Hi guys. Okay, so let's continue on with chapter 7. It's the chemical reactions and quantities. So we are looking at the mole relationships, the mass calculations, limiting reactants in the percentage yield, and the energy in a chemical reaction. Okay, so last time we talked about how to calculate the molar mass, which is the formula mass of the compounds. And now we are going to apply all that information. And also we understood in the previous lecture, what were the moles? So moles are basically the units, and that 1 mole of a substance is equal to the atomic weight of that substance if it's an atom, or 1 mole of a molecule is the molecular weight of that substance if it is a molecule. And if the number of particles that 1 mole contains is 6.022 10 to the power 23, which is the Avogadro's number. So if we are talking about atoms, so it's going to be that many atoms. And if we are talking about the molecules, then it would be that many molecules. Okay, so now let's look at the concept of mole factors. So this is 7.6, and this is the mole factor. So that is the relationship between the two entities. So one example here is, how do we apply these moles in a chemical reaction? So here you have iron, which is in a solid state, reacting with sulfur, which is also in a solid state. And when these two are heated and fused, they give you iron 3 sulfide, which is Fe2S3. Okay, so this is iron 3 sulfide. So iron is in the +3 state. Okay, now let's balance it. So we need 2 irons here, and we need 3 sulfurs on the reactant side in order to make it Fe2S3. So this balances. So one thing is always, as a rule, always balance the equations. Okay, always. So keep this in mind, that always you balance it and check for balancing. So we see that this means 2 moles of iron are reacting with 3 moles of sulfur to give you 1. So this just means 1 if there's no number. So this is how you write this, so there are relationships in this. The relationship between iron and sulfur. Okay. Next is the relationship between iron and Fe2S3. And the third is the relationship between sulfur and Fe2S3. Okay, iron and sulfur. So here we have iron. Iron is 2. So these are the conversion factors. So 2, so let's write this down here, the conversion factors. So we will write the and we are going to look at the, oh God, sorry, I'm going to just move this here down so we can write down the conversion factors. Okay. Okay, EQ. So these are the conversion factors from the reaction. All right, so here we have iron and sulfur, iron and Fe2S3, and Fe2S3 and sulfur. Okay, so we see that 2 moles of iron are reacting with 3 moles of sulfur. Okay, so this is one conversion factor. The second conversion factor is 3 moles of iron, 3 moles of sulfur are reacting with 2 moles of iron. So 2 conversion factors. Okay, here we see that 2 moles of iron are producing 1 mole of Fe2S3, or 1 mole of Fe2S3 is produced when 2 moles of iron react. Okay, these are the conversion factors. Next is 3 moles of Fe2S3 are produced when 3 moles of sulfur react, or 3 moles of sulfur, 3 moles of sulfur are 3 moles of sulfur are reacting to produce, sorry, this is my mistake here. This is 1 mole of, 1 mole of Fe2S3 is produced when 3 moles of sulfur are reacting, and 3 moles of sulfur react to produce 1 mole of Fe2S3. All right, so these are the different conversion factors which can be used to find, if there are unknown quantities. So how to use these conversion factors in the problem. So here we, as usual, that you write down your given, whatever entity is given and whatever units are there, okay, times the mole to mole fractions. So the top moles is the moles that you want. The bottom mole is the mole that you want to get rid of. So this unit, the mole, so here given, because these are just moles, so given moles, okay, and the moles that you want to find, so these are the moles that you want to find, and these are the moles that you want to cancel out or remove, okay, cancel out or remove. Okay, and this is the moles that is given. So if you are given moles of A, then this is going to be moles of A, okay, and this is going to be B. So this is a conversion of moles of A to moles of B. And the language that is written is, so here's the thing, convert, either the question is going to ask you convert moles of A to moles of B. Okay, this is one piece. This is how they will write. Or they are going to say find the moles of B. Okay, and I'm just removing this, moles of B from moles of A. Okay, so this is what that means, that this piece right here is the moles of B is what you want to find, and this is the moles of A from A. That means these are the ones that get canceled out or removed. Okay, so this piece is going to be in the numerator, and this piece is the denominator. Okay, so this is the moles that you want. All right, oh sorry, that you want to remove or cancel. Okay, so keep this in mind, that this is the one that you want to remove. So here, the moles that you want is here, and the moles of A is the one that you want to cancel out. So this is the whole setup. Okay, now let's do this here, this problem, page 262, page 262, and this is the problem, study check. Seven point 7.10. Okay, so here we see, using the equation in sample problem 7.10, calculate the number of moles of iron needed to react with 2.75 moles of sulfur. So you are given 2.75 moles of sulfur, and you're being asked calculate the number of moles of iron. So calculate means find. the number of moles of iron. Okay, so this is what you need to find. So using the reaction, using the balanced equation, and let me write this down again, using the balanced equation and above conversion factors. You set up the problem here using the balanced equation and the above conversion factors. So we see that from this thing you are given, so write down you're given 2.75 moles of sulfur. Okay, 2.75 moles of sulfur multiply by, now this is the mole to mole ratio, and this mole to mole ratio is coming from the balanced equation. So we see that 2 moles of iron are reacting with 3 moles of sulfur. So we want to get rid of sulfur. So 3 moles of sulfur is in the denominator and 2 moles of iron is in the numerator, because this is iron is what we need. We want this, and we want this, and we want to cancel this out. Cancel out or remove. Okay. Oh, cancel out. Okay. So we see here that the moles of sulfur and moles of sulfur cancel out, and you're left just with the moles of iron. So this is the moles of iron is what you want. So this piece right here is coming from the balanced equation. So this is also called mole to mole ratio. Let me put this here. This is also called mole to mole ratio or molar ratio, molar ratio, mole to mole ratio. Okay, and this is coming from the balanced equation, from the balanced equation. Okay, so that's why it's very important to balance the equation, and the rest is just pure math, which is 2.75 multiplied by 2 and divided by 3. Okay, and so these are actually moles of iron, and this is going to give you the answer of 1.83 moles of iron. Okay, so this is the way you were going to do these problems. I can do one more here. Let's look at the one example, 7.60. Okay, and this is on page, this is the problem from the section, and this is on page 263. Page 263. Okay, so here you are given this problem, or given this reaction, N2 as a gas reacting with 3 moles of hydrogen as a gas, and this gives you 2 moles of ammonia, NH3, as a gas. Okay, now how many moles of hydrogen are needed to react with the moles of nitrogen? So 1 mole of nitrogen, so here's the, this is, I'm going to just write this down here, 1 mole of nitrogen is reacting with 1 mole of nitrogen is reacting with 3 moles of hydrogen to produce 2 moles of ammonia, NH3. Okay, so this is the way you look at the reaction. Okay, so let's do part B here. So how many moles of hydrogen are needed to react with 1 mole of nitrogen? For 1 mole of nitrogen, it's 3. So this is part 1. Part B is how many moles of nitrogen? How many moles of nitrogen react with how many moles of nitrogen react if if 0.60 moles of ammonia is produced? How many moles of nitrogen react if 0.60 moles of NH3 are produced? How many moles of nitrogen? How many moles of nitrogen react if 0.60 moles of ammonia are produced? So write down the given. Given is 0.60 moles of ammonia. Okay, times. Now you have mole to mole ratio. So we see that 2 moles of ammonia are produced when 1 mole of nitrogen reacts. Okay, so here in this case, you see that the moles of ammonia and moles of ammonia cancel out, and you're just left with the moles of nitrogen. So we will just put here 0.60 times 1 mole of nitrogen, because that's the unit that's left, divided by 2 moles of ammonia, NH3. And so here the answer comes out to be 0.30 moles of nitrogen. Okay, so same as the case is the part C. The question is how many moles of ammonia are produced? So we need to find the moles of ammonia that are produced, and you're given 1.4 moles of hydrogen. Okay, so what will you do? You are going to put 1.4 moles of hydrogen on one side, that is given to you, times you're going to bring in the mole to mole ratio, and that mole to mole ratio is hydrogen is going to be at the bottom, and you need nitrogens, the ammonia, so that's going to be on the top. And now you're going to look at the balanced equation. So the relationship between hydrogen and ammonia is 3:2. So in other words, 3 moles of hydrogen are producing 2 moles of ammonia. Okay, so this way, when you set this up, you see the moles and moles of hydrogen cancel out, and you're just left with the moles of ammonia. And this is the one that you need to, this is your want. And this is what you want. The want stays on the top, and the given cancels out through the conversion factor. And this conversion factor is the mole to mole ratio coming from the balanced equation. Balanced, that is why balancing is important. Balanced equation. Okay, so now we are doing what? We are going to take 1.4 multiply by 2 divide by 3. And what do you get here? These are the 2 moles of ammonia. So, okay, so the answer comes out to be 0.933 moles of ammonia. Okay, so this is how you use the conversion factors in determining the moles of one entity when the moles of the other entities are given. But in case you're not given the moles, you're given the mass, then in that case, what do you do? So let's look at this. This is the next piece is the mass to mass conversion. Mass to mass conversion. Okay, so whether it's a mass of a product, whether it's a mass of reactants, so it's all those. Okay, so let's look at the study check. Study check problem 7.11, and this is page, so let's write this down here. Page 264. Page 264, study check 7.11. Using the equation in sample problem 7.11, and the sample problem is you are given 2 moles of C2H2, and this is ethylene. Oh, no, sorry, acetylene. This is a gas. When it is combusted in air, that means with 5 oxygens as a gas, and it's a combustion reaction, so this is the sign of heat. It gives you 4 moles of carbon dioxide as a gas, plus 2 moles of water, 2 moles of H2O as a gas, and then of course a massive amount of heat is also produced here, but we are going to look at the heat reactions later. But right now, this is the given equations. So you see, either it's going to be already balanced for you, but you can also check balancing if there is no typo error, or sometimes things don't get like published, printed or something. So anyway, so here is the roadmap you're going to do. First of all, the roadmap that you're going to follow is you're going to take the mass. So basically, if you're converting whatever the 2 entities are, it's always going to be 2 entities. So A needs to be converted to B. The grams of A needs to be converted to the grams of B. So it looks like a gas, but the grams of A needs to be converted to the grams of B. So what are we going to do here? So this is going to be your roadmap, which is you take A, grams, convert that to the moles of A. So let's put this here. So grams of A is converted to the moles of A. So grams of A is converted to moles of A using the molar mass of A. Molar mass of A. Okay, then that converts to the moles of A. Next is you're going to look at the moles-mole ratio. So because you want to convert to B, so that means the moles of B is going to be on the top over, this is the dimensional analysis, over the moles of A, which is at the bottom. Okay, this piece is coming from the balanced equation. So in other words, A gets ruled out. So you're left just with the moles of B. Next thing is you're going to convert the moles of B to the grams of B. And how do you do that? You're going to take the molar mass of B, and that molar mass of B is basically grams of B over 1 mole of B. That's what it is. Okay, so that's going to give you, so that basically when you set it up, so the moles of B cancel out and you're just left with the grams of B. So you see that this, you start with A and you get the B, but A and A cancels out, and then you have converted the grams of A to the moles of A. Moles of A has been converted to moles of B. Then the moles of B cancel out. And using the molar mass of B, when you cancel the moles out, you get the grams of B. So this is your basic, formula or the strategy. Okay, so now let's look at this problem. Using this equation, so you are given, oh, sorry about that. All right, so you are given 25 grams of oxygen. So given 25.0 grams of oxygen. Okay, using this equation in sample, calculate the grams of CO2, and we need to find the grams of CO2. How many grams of CO2? Okay, can be produced when 25 grams of oxygen react. So here are a few things you need to pay attention to. In this case, we're looking at only the relationship of oxygen and carbon dioxide. So here is this oxygen and here's the carbon dioxide. So always check the balancing. Let me write this again. Check for balancing, balancing. Check for balancing first of all. So we see there is a 5-to-4 relationship. So that 5 moles of oxygen are giving you 4 moles of CO2. So let's do this, a few things here. So in this case, always first check for balancing, and if it's not balanced, you balance it. Okay, next is, second is, you are going to focus only on 2 entities in question. So 2 entities in question, which ones are those? We had, in this case, oxygen and carbon dioxide. Next is find the molar mass. Remember, we are going to be converting the grams to moles and moles to grams. So molar mass of each, molar mass of the 2 entities that are in question. So I'm going to just put this here. 2 entities in question. Leave the rest. Okay. So next is, fourth is, then focus on or look at the mole to mole ratio in the balanced equation. Mole to mole ratio in balanced equation. Okay, in balanced equation. All right, so now we are doing this. We are going to take molar mass of oxygen. So oxygen, so there are 2 oxygens, each is weighing 16 grams. So we are going to get 32 grams per mole. That's the molar mass of oxygen. Okay, that's one piece. Next is for the CO2. Then CO2, there is 1 carbon, and carbon is 12 grams, and there are 2 oxygens, and each oxygen is 16 grams. So we are getting 12 grams here and 16 to the 32 grams here. So we get 4 and 4, 44 grams per mole of CO2. All right, now we are going to write this down here. The given 25 grams of oxygen. So write down your given 25.0 grams of oxygen. So the first step is to convert grams to moles. So 1 mole of oxygen is 32 grams. This is the molar mass, 32 grams of oxygen. Okay, so this is the conversion grams to moles. Next is the mole to mole ratio. So we see that from the mole to mole ratio that there are, what was that, 5-to-4. So 5 moles of oxygen are producing 4 moles of CO2. Okay, next is we need the grams of CO2. So we know that 1 mole of CO2 is 1 mole of CO2 is 44 grams of CO2. Okay, so you will set this thing up, and here you're going to take the grams of O2, and grams of O2 cancel out. Moles of O2 and moles of O2 cancel out. Moles of CO2 and moles of CO2 cancel out. And you are only left with the grams of CO2, and this is what you need to find. Okay, this is what you found. So the rest is just math. So 25.0 times 1 times 4 times 44 times 44 divided by 32 times 5 times 1. And this gives you the answer, and that's 44 moles of CO2. And this should give you the answer Just give me 1 minute. Let me finish the calculation. Okay, so this is what you get. 4400 divided by 160, and that is 27.5 grams of oxygen, CO2. Okay, so that is your answer. So, you know, the whole bunch of it is just the same thing, grams to mole, moles, then mole to mole ratio, and then the molar mass. So this piece, like again, I said, this is coming from the balanced equation, comes from balanced equation. So you are going to then just follow this strategy and you should be okay. All right. All right, so I'm just letting you know that on the exam, definitely there is going to be a question on the test from here. All right, okay. All right, next is the limiting reactants and the percentage yield. Okay, the limiting reactants. Limiting reactant. And percentage yield. Percentage yield. Okay. Calculating the moles of the product from the limiting reactant. So first of all, what is a limiting reactant? So here is, let us say, pieces of bread. So let me just make it, and then I will, start the recording again. Okay, so let's look at this scenario in which we see that we have these slices of bread. Okay, we have a bread. These are the slices of bread. So slices of bread, and how many there are? In this case, we have 6 of them. So when we make a sandwich, you know, one slice over the other. So that's how we make the sandwich. So in this case, we can only make 3 sandwiches, right? There are six slices of bread, and we can only make 3 sandwiches. And we have lots of cheese, right? So lots of cheese slices are present, but technically we can only make 3 slices of bread. Therefore, 3 slices of sandwich, three sandwiches. Therefore, the bread becomes the limiting reactant. Okay. On the other hand, you have lots of bread, but you have only 2 slices of cheese. Okay, so here this is only 2 slices of cheese. So how many sandwiches can you make? Only 2. So these 2, so that is why this in this case, in the second case, the limiting reactant is the cheese. But limiting reactant is dynamic. It changes. You can bring in more slices of cheese and as many as there are pieces of bread, and then you can have like that many sandwiches. Or you can have, in the first case, you can bring in more bread and then you can have more sandwiches in that case. But then it can change also, so it depends which entity is more and which entity is less at that point and what you can produce. So the final product is the sandwich. Final product is the sandwich. And the reactants are the slices of cheese and the bread, pieces of bread. And depending, which one is less, that is obviously going to give you the less product. So limiting reactant is the one that is lesser, that gives you, not lesser in quantity, but which gives lesser product. Okay, now let's look at this scenario here in which we are doing moles of the product from the limiting reactant. So this is page 267 and we are looking at problem. This is page 267 and this is problem, study check problem. Study check problem. Study check problem 7.12. Okay. So here is a problem where we are given the carbon monoxide. So carbon monoxide as a gas is reacting with 2 moles of hydrogen as a gas. Okay, and this gives you the methanol CH3OH. And this is, in this time, it's in the fumes in the gaseous state. So this is called the methyl alcohol or methanol. Okay, it's an organic compound. Okay, so here in this balanced equation, we see that 1 mole, this is 1 mole, this is 2 moles, and this is 1 mole. So that's one piece. All right, now let's look at if the initial mixture of the reactants in the sample problem contains 4 moles of carbon monoxide. If there are given, so you are given 4.00 moles of carbon monoxide, okay, and 4 moles of hydrogen and 4.00 moles of hydrogen. Okay, what is the limiting reactant and how many moles of methanol can be produced? So the question is, what is the limiting reactant? And second is, how many moles of methanol can be produced? How many moles of CH3OH produced? Okay, so obviously the one that's giving you the lesser methanol will be the limiting reactant. So here let's find out. So it's just a mole to mole conversion. Okay, so just using the moles to determine, which one is producing less. So here, keep this in mind, very important. The relationship of carbon monoxide to methanol, CH3OH, and then the relationship of hydrogen to methanol. So these are the 2 reactants and, these are the 2 reactants and we will see, which one is giving you the less methanol. So mole to mole conversion. And here we see that from the given 4.00 moles of carbon monoxide times the mole to mole ratio. So from this equation, we see that 1 mole of carbon monoxide is giving you 1 mole of methanol. So 1 mole of CH3OH, and then the next is the 1 mole of carbon monoxide. Okay, and you stop here. So this is going to then give you when you see that the moles of carbon monoxide and the moles of carbon monoxide cancel out, and you're left with just the moles of methanol. So we have here 4.00 moles of CH3OH are produced when 4 moles of carbon monoxide react. Okay, next is, let's look at the next scenario where you have taken, so this is again, let's put this some number here. Oh, sorry. Okay, so here we have 4.00 moles of hydrogen times. We see from this equation that 1 mole of methanol is produced when 2 moles of hydrogen react. So 2 moles of hydrogen reacting to give you 1 mole of CH3OH. Okay, so we see here that the hydrogen and hydrogen cancel out, moles of hydrogen and moles of hydrogen cancel out, and you're just left with the moles of methanol. So we have 4 moles times 1 divided by 2. So roughly, so in a way that you're producing 2.00 moles of methanol, CH3OH, are produced. So which one is the limiting reactant? So in this case, because hydrogen is producing less, 2 is less than 4. So let's write this down. 2 is less than 4. 4 is more. So lesser CH3OH produced. Okay. Therefore, hydrogen is the limiting reactant. Okay. So this is how you do the mole to mole conversions. All right. Now, in case you're given the mass, so it's the same thing as what we discussed. Let's look at this study check problem 7.13. Okay. Now this is the mass to calculating the mass of the product from a limiting reactant. So basically it's the mass to mass conversions. So here you have, mass to mass conversion. And this is based on the same strategy we discussed earlier, mass to mass conversion. Okay, so here you have, okay, study check 7.13, and this is page 268, page 268, study check 7.13. Okay, hydrogen sulfide burns with oxygen to give sulfur dioxide. So here's this equation, 2 moles of H2S in the form of a gas, and these are reacting with 3 moles of oxygen as a gas. Okay, and that gives you, on heating, 2 moles of sulfur dioxide as a gas and 2 moles of H2O. 2 moles of H2O as a gas. All right, so this is the balanced equation already given. Okay, how many grams of sulfur dioxide are formed? So the question is, how many grams of sulfur dioxide are formed from a reaction in which 8.52 grams of H2S. So you are given 8.52 grams of H2S and 9.60 grams of oxygen. All right, so what do you do here? Here we are given this. So what do? We are looking at the relationship of H2S to sulfur dioxide, and we are looking at the relationship of oxygen to sulfur dioxide. And why are we doing that? We are going to find the limiting reactant. And based on that, we will know how much of the sulfur dioxide are we forming, because you can only produce, based on how much of the limiting reactant is there. Okay, so here you have to find, first of all, the molar masses. So the molar masses, because it's all going to be grams to mole conversions, those things. So H2S is 2 of hydrogens, 1 of sulfur, and hydrogen is 1 gram and sulfur is 32 grams. So this gives you 2 and this is 32. So this is overall 34 grams per mole. So that's for H2S. Next is for SO2. So you have 1 of sulfur, and the weight of the sulfur is 32. As you can look in the periodic table, look at the mass number, and that is 32 grams. So this is grams. This is from the periodic table. So this is grams, this is grams. Okay, then comes the 2 of oxygens, and each oxygen is 16. So you have 32 grams here, and you have 32 grams coming from the oxygen. So that makes us 64 grams per mole. So this is for H2S, and this guy is for SO2. Okay, remaining is oxygen. Oxygen is O2. O2 is 2 oxygens. Each is 16 grams. So this is 32 grams per mole of oxygen, O2. Okay, so these are the, these are the molar masses that we will be needing. So put them on the side somewhere, always. All right, next is, let's look at the relationship of H2S to SO2. So H2S to SO2. So we are given 8.52 grams of H2S. So write down 8.52 grams of H2S, convert that to moles. So times 1 mole of H2S divide by the H2S alone is, H2S is 34. Sorry. Okay, H2S is 34 grams of H2S. Okay. Times the mole to mole ratio. So H2S is going to be at the bottom, and we are interested in sulfur dioxide. So that's on the top. And we see that 2 moles of sulfur dioxide are produced when 2 moles of H2S react. Next is convert. You can stop here, but you can, we'll just carry on because we want to convert the grams. We need to find the grams of sulfur dioxide. So 1 mole of sulfur dioxide is 64 grams of sulfur dioxide. Okay, so this way you see that the grams of H2S, moles of H2S cancel out, moles of sulfur dioxide cancel out. Okay, so you are just left with these numbers: 8.52 times 1 times 2 times 64 divided by 34 times 2 times 1, and whatever answer you get, that is going to be the grams of sulfur dioxide. Let's calculate that. Okay, so I finished this recording. I finished this calculations. So we see that 8.52 times 1 times 2 times 64 divided by 34 times 2 times 1 gives you 1090 divided by 68. That is 16.2 grams of sulfur dioxide is produced when 8.52 grams of sulfur of H2S is used. So that's one piece. Now let's continue on with the oxygen and sulfur dioxide. So here is this relationship of oxygen to sulfur dioxide. And here we have oxygen is, how much was that? 9.60. So 9.60 grams of oxygen. First step is convert to moles. So we know that 1 mole of oxygen weighs 32 grams of oxygen. You calculated these weights right here. Okay, so these are the molar masses. Okay, next is look at the mole to mole ratio of oxygen to sulfur dioxide. So sulfur dioxide moles and oxygen moles. So look at the equation, and we see here that it's 3:2 ratio. So 3 moles of oxygen, 3 moles of oxygen, and 2 moles of sulfur dioxide. 2 moles of sulfur dioxide. Okay, so 2 moles of sulfur dioxide times, now 1 mole of sulfur dioxide, the weight of that is 1 mole of sulfur dioxide is 64 grams. So put here 64 grams of sulfur dioxide. So here we see now that the grams and grams, oxygen and oxygen cancel out. We see the moles of oxygen and the moles of oxygen cancel out. Moles of sulfur dioxide cancel out. And what do you get left here? You are left with 9.60 times 1 times 2 times 64 over 32 times 3 times 1. And that gives you the answer. 1 minute. Okay, so we see that when you finish the computation, we get the grams of sulfur dioxide to be 12.79. Okay, so that's the grams of sulfur dioxide. Here, grams of sulfur dioxide. Okay, so 12.79. So out of this, if you look at it, the H2S is less, but it's giving more sulfur dioxide. So that's in calculated yield. This is just a calculated yields. Both of them are calculated. So it's just numerically, it comes out to be like that. Next is oxygen is larger in amount. If you look at it, this is larger in amount, 9.60, but it's giving you lesser. So this becomes the theoretical yield. So no matter, what with the amount that gives you, the entity that gives you the lesser product is always going to be the theoretical yield. So theoretical yield is, in theory, yes, if all goes well, if all goes well, then the theoretical yield is 12.79. Okay, so that kind of question can be asked. So I'm going to just put it here that the limiting reactants problems are going to be on the test. So all these conversions, definitely they will be on the test. Okay, all right. So here is your next problem, which is on the percentage yield. And I have to start my office hours. So therefore, I'm going to just leave it this here, and then we are going to go make another video on the energies. Okay, so let's look at the next one is the percentage yield, PERCENTAGE. Okay, let's just put this here. Yield. Okay, now when we talk about the percentage yield is in, there is a productivity loss in the reactions. Productivity loss of final product. Okay, so final product is what we need, but the final product is always going to less. So due to steps in reactions, processes and so forth, different processes, so you lose. So there is the actual yield is what you get in your hand after you have finished all the steps. So actual yield is final yield, and this final yield is always going to be lesser than the theoretical yield. So actual yield is in reality what you obtain in your hand after you've finished off all the steps. So actual yield technically is always going to be less than the theoretical yield. Okay, is always going to be less. So the formula that is used is percentage yield is equal to the actual yield over the theoretical yield. Okay, so in these, small videos that I post on YouTube, and the links of which are in the Canvas, those YouTube videos go a little bit more detailed on what the applications are and so forth. So you can, look at that content if you need to, but let's look at this problem for now. That is page 270. Okay, and this problem 7.14. Problem 7.14. Okay, so here we have for a reaction in sample 7.14, what is the percentage yield of the lithium bicarbonate if 8 grams of carbon dioxide produce 10.8 grams of lithium carbonate? So let's write down this reaction first. They are referring to lithium hydroxide. Sorry, so the reaction is lithium hydroxide as a solid is reacting with carbon dioxide as a gas. and this gives you lithium bicarbonate, LiHCO3, which is a solid. Okay, and so it's one-to-one relationship, and so all those things. So that's fine. Next is, as usual, let's just do this here, that lithium bicarbonate is the 1 mole of lithium bicarbonate. So the molar mass of lithium, LiHCO3, is equal to 67.96 grams. Okay, and molar mass of lithium hydroxide is equal to 23.95 grams. All right, so okay. For the reaction in this sample, what is the percentage yield of lithium bicarbonate if 8.00 grams of CO2, sorry, I forgot to write down the molar mass of CO2, the molar mass of CO2 is equal to the, I think it's 44, so carbon is 12, oxygen is 16, 32 plus 12, 44. 44 grams, sorry, this is grams per mole and grams per mole. Okay, now we have here, for a reaction in sample, what is the percentage yield of lithium carbonate if 8 grams of CO2, so we are looking at the relationship of CO2 to lithium bicarbonate, produces 10 grams. So you are saying that if you are given 8.00 grams of lithium bicarbonate and it is producing 10.5 grams of lithium bicarbonate, then find the percentage yield. So here's a very important piece. This piece that is given to you, this is the actual yield. This is actual yield. They are not saying it, but that is what it is. This is the actual yield. Okay, so when you use 8 grams of lithium bicarbonate, you produce 10.5. So first, always, this is not stated, but first always find theoretical yield. Okay, now what is that? First, always find the theoretical yield. So here you are given CO2, which is 8 grams. So let's do this. 8 grams of CO2, 8.00 grams of CO2, as usual, as we have been doing, convert that to moles. So 1 mole of CO2, and that is 44 grams of CO2. Okay, times, now the mole to mole ratio, 1 mole of CO2 is producing 1 mole of LiHCO3, lithium bicarbonate. Okay, and next is 1 mole of lithium bicarbonate, LiHCO3, is 67.96 grams, 67.96 grams of lithium bicarbonate. So what do you see here? We see that grams of carbon dioxide cancel out, moles of carbon dioxide cancel out, moles of lithium bicarbonate cancel out, and you're just left with the grams of lithium bicarbonate. So now let's just do the math. 8.00 times 1 times 1 times 67.96, divide that by 44 times 1 times 1, and let us see what you get. Okay, so we see that when you do the math, you see that 543.68 divided by 44 gives you 12.35 grams of lithium bicarbonate. Okay, but the actual yield Actual is different. So what you have calculated here is the theoretical yield. This is the theoretical. So in theory, when you calculate, you would get 12.35 grams, but actual yield is lesser, and which is fine. So write down the formula. The question for finding the percentage yield is equal to the actual yield. Always write the formulas over the theoretical yield. Okay, times 100%. So did I write this down here? Actually, sorry, this is times 100%. Okay, all right, so now we are going to put our actual yield, which is 10.5 grams, that is given to you. So 10.5 grams divided by, in theory, you have 12.335. So 12.35 grams times 100%. Okay, and this comes out to be 84.7%. So this is the percentage yield. So I'm just letting you upfront that, yes, there is going to be a question on percentage yield on the test. Okay, so I'm going to stop here because I have the office hours starting already, and we'll continue on with the calculating the heats of the reaction. I'm going to just see if I can do it tonight or it'll be done tomorrow. All right, guys. So thank you for watching. You have any questions, don't hesitate to ask me. Okay, thank you. Bye-bye.